All right, looks like we're 20 minutes after the hour, so we're going to get started back here. As I said on the last session, if you were on that, this is shifting gears a little bit to get into some of the event streaming capabilities. And we have Neeraj Ladd from... All right, looks like we're 20 minutes after the hour, so we're going to get started back here. Okay, hang on. As I said on the last session, if you were on that, this is shifting gears a little bit to get into some of the event streaming capabilities. And okay, sorry about that. So just to say that we get started here, and then there'll be some questions at the end of the session. But let me get out of the way and turn it over to Neeraj. Take it away.
Hello, and welcome to this session in IBM TechCon 2025. I'm Neeraj Ladd. I'm the architect for IBM Event Streams, which is an operator-based offering for deploying and managing enterprise-grade Kafka on Kubernetes. If you aren't using Event Streams already, it's a capability that you can use with Cloud Pak for integration or event automation licenses if you've got any of those. Today, we're going to talk about one of the most significant architectural changes in Kafka in many years, and that is removal of Zookeeper. So let's take a quick look at the agenda. So we'll start with taking a brief overview on what Zookeeper is, and then we'll go on to look at how Kafka uses Zookeeper. We'll move on to figure out what are the challenges introduced by this architecture and the solution that was introduced in the Kafka community in the last year or so. This is called KRaft or KRaft, whichever way you want to call it. We will finally move on to look at what the migration path looks like. If you are using Kafka with Zookeeper, how do you move on to a KRaft-based Kafka? And finally, we'll look at how Event Streams users will be able to do that migration and benefit from this new capability. Right, let's move on to Zookeeper. So Apache Zookeeper is a high-performance open source coordination service for distributed systems. With any distributed applications, you need a mechanism to share configuration and coordinate what's happening with various components that are spread across different places. Zookeeper provides such a service, and what this means is every distributed application doesn't need to implement their own synchronization or coordination service. They can hook into Zookeeper and store the information they want, and then other pieces of your distributed application can read from Zookeeper and provide, get the information they want, which is a great idea. And Zookeeper has some massive benefits to, especially how it manages coordination. So if you look at this, there are a number of Zookeeper servers. Zookeeper itself is replicated as well. So you have a leader and a bunch of other Zookeeper nodes that follow and establish a consensus. And the information that's stored in Zookeeper is stored in a hierarchical structure, as it's shown in the picture here. It'll become a little bit clearer as we go on. Some of the key benefits of Zookeeper: it uses a shared hierarchical structure or a namespace, which is very similar to a file system. And this makes it very easy for applications to access and read and write files because they are pretty much used to storing information locally in a file system and how we go from there. It is available. So like I said, like the distributed systems, it coordinates. Zookeeper itself is replicated over an ensemble, and ensuring the availability is key to any of those systems. So if one of the Zookeeper nodes goes down, one of the other nodes will become the main primary or the leader, and then the system will continue working. So it provides a highly available coordination service. Zookeeper is ordered, so as things change over time, there's a timestamp attached to each of those updates, and this helps in the applications which are consuming this service to keep track of the order in which things have happened. And lastly, it's fast. Data is kept in memory, and it can achieve a very high throughput with low latency. So everything about Zookeeper is perfect from that point on. Now let's look at how Kafka uses Zookeeper here. Apache Kafka uses Zookeeper for storing and replicating metadata of the brokers and topics. Now, since inception, Kafka has always used Zookeeper to store the cluster metadata, be it brokers, controllers, what topics we've got, how many partitions are there, which are the leaders and followers, in-sync replicas, all of that stuff. And this is fundamental to ensuring a consistent view of everything within the cluster. And Zookeeper basically provides that capability. Now, if you look at a typical Zookeeper example, you've got a Zookeeper cluster or an ensemble, and the Kafka clusters or the brokers have one of them identified as the controller, and that controller is responsible for communicating with the Zookeepers. The others also will fetch, but the controller takes the primary role in writing and coordinating most of the work here. And then the controller replicates the information it's got from Zookeeper onto the other brokers. That's typically how a Kafka cluster would work. Now let's look at the key aspects that Zookeeper does here. So broker management. So as new brokers join or leave the cluster, the information is stored in Zookeeper, and it'll become the controller or record all the activities like that. When one of the brokers, like the controller, I just showed in the previous picture, when the controller leaves, a new controller needs to be elected. That is again a responsibility that Zookeeper performs, and it performs that by issuing a new event that all the other brokers receive, and then they start participating in becoming a controller, and then an election happens. All the topic information or configuration, like topics and partitions, is all stored in Zookeeper. Consumer groups, Zookeeper also is used for tracking consumer group members and their topic subscriptions. So it knows which consumers are reading which topic and so on. And lastly, the permissions and quotas. So it maintains all the ACLs and client quotas that decide who can access which topics and limits the resources. So I'm hoping that this makes it pretty clear that Zookeeper is the authoritative source of all metadata within a Kafka cluster. So any critical information that you believe the brokers need is typically stored here, as long as it's the metadata that the cluster needs. So if everything's so great, why replace Zookeeper? Let's look at the fundamental here. So the problem is not with Zookeeper itself. The problem is with the architecture or the approach of an external metadata management system. You've got a Kafka cluster, which is managing its own state and doing stuff, but there is an external system which is managing the state of all the metadata that's stored there. So if I go and look at the significant challenges here, the first one is the architectural complexity. We've got two different or distinct systems that have duplicate architectural pieces, components, security models, configuration, that kind of stuff. So it makes it harder architecturally to make sure things all line up. That, for example, they all need to support the same sort of security models and things like that. In terms of the operational overhead as well, when you are deploying and managing a Kafka cluster, you have to take on the responsibility of managing and deploying a Zookeeper cluster. So that adds an additional burden. And also these two systems have slightly distinct configuration. So there is a separate Zookeeper configuration that you maintain than a separate Kafka configuration. So that this causes more complexity and burden in terms of how you manage a Kafka cluster with an external Zookeeper. Obviously, it's an external project. So Apache Zookeeper and Apache Kafka are two distinct open source communities. While they are both in Apache, they are still two different projects, and it requires some sort of planning or coordination to make sure that things are lining up. When new features are added or things are changing, that everything lines up and releases are coordinated in time and that sort of stuff. So that makes an external dependency harder to manage. And also there's a level of double caching that could happen because Zookeeper is trying to reflect some sort of data and caches the information about the metadata that it stores. And Kafka controller is also trying to do that and trying to maintain that. So there's some level of duplication here. There, like, other than those general architectural and operational burden and things, there were a couple of very specific issues with the Zookeeper model, and they're all around the scalability and performance availability type situation. So let's take a quick look at these. So let's consider the broker shutdown. When a broker shuts down, the controller has to update the metadata for every partition that was on that Kafka broker. With respect to which the leader is, who the followers are, how many are in sync replica, and it updates this information in Zookeeper. Then it tries to fetch the updated information back from Zookeeper and then propagate it to all the other brokers one at a time. So if you have many topic partitions on a particular broker, when that broker shuts down, this process can take longer and longer, and it was starting to become a limiting factor on how many partitions you could host within a Kafka cluster. Similarly, when a controller goes down and a new broker needs to become a controller, it has to read the entire state of the cluster from Zookeeper again, because the current state is maintained mainly in the controller. And again, as the metadata grows, this cold starts or loading from scratch can be taking longer and longer. And as a result, until the controller is there, it can't really serve other requests. So it starts impacting the availability of controller in case of a failover. And lastly, as we saw in the previous picture, controller is the one that's doing most of the read writes from the Zookeeper, and that can become a bottleneck with a large number of partitions as well. So these couple of scenarios were pretty prominent and starting to bother the Kafka community, and that's why they've thought about, okay, let's try and change this. And that led to a Kafka improvement proposal, or KIP 500. Now, KIP 500 was the first proposal that introduced the concept of removing Zookeeper and managing state as an internal event log. There were a number of follow-up proposals. I've not mentioned them here, but there are a number of other proposals that go on to more granular details on what is the structure of the data that's stored and things like that. But we don't need to worry about that at the moment. So KIP 500, and there's a link here. So if you want to later on go and follow the proposal, you can go and have a look. Is a proposal from the Kafka community to remove Zookeeper for primarily two reasons. So simplifying the configuration and deployment. So like we said, the configuration of Kafka and Zookeeper are two different things, and simplifying that was one of their main objectives so that they can remove the dependency. It also would allow Kafka to manage metadata in a more scalable and robust way, enabling supporting more partitions. Now, Kafka manages topic state as an event log. We know that that's how topics and their replicas work. But Kafka itself, while Kafka's users are benefiting from this approach, Kafka itself has been left out because Kafka is not using the same approach today in the Zookeeper world to manage its metadata. And this led to the idea that the cluster metadata should be stored in Kafka itself instead of a separate system like Zookeeper. And what this does is avoids problems associated problems and discrepancies that could arise when the controller and the Zookeeper state aren't matching. Rather than pushing out notifications to brokers, which is what happens in the Zookeeper world, brokers can simply consume metadata events from the event log. Right? That's how the typical replication happens for a normal Kafka topic. Brokers will be able to store metadata locally in a file, and when they do that, when they start up, they will only need to read what has changed and not the full state. So this helps Kafka quickly get back and optimize the information stored in a way. Now, what is KRaft? KafkaRaft or KRaft it's an event-based implementation of Raft consensus protocol. Raft is a consensus protocol for managing a replicated log. It's an independent thing. It's not like a new invention from Kafka, but Kafka has basically implemented an event-based, added an event-based implementation of this Raft consensus protocol. One thing to note is it is still based on consensus. So for consensus, you have an odd number of people or entities that are participating. And as long as majority agree on something, that is the answer. That's kind of the consensus. That's how Zookeeper worked as well. And KRaft is no different. It is also based on consensus, but it is different to Zookeeper in some of the aspects. First one being there are multiple controllers. So if you look at this is a KRaft based deployment. Instead of having a single controller, we now have a number of controllers, and the rest of the brokers are and the two followers are all following this active one. So where we had a leader or a controller, a single controller, we have a number of controllers. One of them is the active controller, but other controllers and the brokers, which are also called observers in this instance, are all just following and fetching the metadata from the active controller. And this is typically how Kafka topics get replicated as well. There's one significant difference here, though. When you are replicating, let's look at the store first, and I'll come back to that. So when we said manage the metadata internally, what Kafka have done is they've introduced a new special internal topic. It's a single partition topic called __cluster_metadata. And this is the topic that Kafka uses now for storing all the information that previously used to be in the Zookeeper, essentially. And the active controller writes metadata or events to the topic. All the other controllers, which are followers, and the brokers, which are observers, replicate the metadata events regularly. And they all update their cache from the committed logs. So think about a topic. The topic is being replicated to all the brokers, but the brokers are also loading that information in their cache so that it's ready and available for them to use. The difference that I was talking about, the replication, is here. So for replicating the metadata with KRaft, we use a quorum replication, whereas for a normal Kafka topic, Kafka uses a primary backup replication. And the difference between these two is with a quorum-based replication, as long as the majority of replicas acknowledge that a write has been done, it is considered successful. Whereas with a primary backup replication, the primary requires acknowledgements from a specified number of brokers, and that would be whatever your in-sync replicas are and things like that. So that's kind of the difference between the two. Kafka now has two different approaches for replicating topic data and replicating its own metadata. The next piece is, okay, now Kafka stores this as a topic, but it'll still keep on growing over time, and it'll become harder and harder for brokers and things to manage. So they've added another change here, and that is to use snapshots and truncation to control the log size. Now, snapshots basically, periodically, they will take an in-memory, it'll take a snapshot of the in-memory data that we've got and store a snapshot which only has one entry per key to optimize cold starts. So by saying one entry per key, we mean that a single snapshot should be able to give you like the latest information that exists today. It doesn't need to know last 3 changes that happened to this particular topic, for example, or this particular entity. And by doing that, what it means is when you have to make a cold start and load everything from the beginning, because you can't really avoid that, then you only have to read the snapshot and whatever else is in your current metadata log, which is a much smaller set than loading everything that's ever happened from on the cluster in that way. So the controllers create snapshots of the in-memory data, And once you have a snapshot, the log is truncated from the beginning up to that snapshot. So you always have the snapshot plus whatever is the delta after it. And after a period of time, there will be another snapshot, and then the log will move on from there. So this allows the logs to be a manageable size and helps with the efficiency side of things. Okay, so as a summary, KRaft metadata is stored as an internal topic and managed via internal quorum of controllers. Now, let's look at the roles that Kafka nodes play. I know we've said controllers and brokers are all internal to Kafka. So here's an example of you've got 6 Kafka nodes here in this picture. 3 of them are the brokers, and that's kind of your data plane, essentially, where the topic data is moved around and replication and all of that. And 3 of these nodes are controllers. And these are the ones that are controlling the metadata and how the topics move and stuff like that. So in this case, every Kafka node has a distinct role or a dedicated role. It's either a broker or a controller. There is another mode possible, although that's not really recommended for production users. So for production, Kafka recommends that the controllers and brokers are kept separate. So you don't have that much benefit in terms of footprint. A lot of people think like, oh, Zookeeper is going away, so I don't need 3 extra pods. That's not quite the reason why they've done this. So the production use case, they would still recommend the same odd number of pods to run your controllers, and you will have the number of brokers that you used to have previously. But it is possible for you to run with shared roles, and that's typically a recommendation for smaller development test clusters. So in this case, you can see there are same number of nodes, 6 nodes, but some of these nodes have dual roles. They are a controller and a broker. And this just means that I could have potentially reduced this to just 3 Kafka nodes, which are all controllers and brokers, and that could be the smallest Kafka cluster you could start with. So you get rid of those. But this mode is only recommended for dev and test type environments. So please bear that in mind. Okay, so let's look at like the benefits of KRaft now. So much simpler architecture. It simplifies the overall architecture as there are much less parts moving here. No need for a separate Zookeeper cluster and a coordination service. There's also a single consistent view for the configuration, the failure scenarios, and security mechanisms supported. So from architecture point of view, it massively simplifies the Kafka architecture. In terms of operations as well, it's much simpler. There's no need for you to monitor an additional Zookeeper cluster, have separate Zookeeper configuration files, and so on. There's no external dependency on another project, so you don't need any coordination with respect to release timelines, new capabilities, or security fixes, or whatever it might be. And lastly, it's a much quicker and lightweight start. So if anybody's been running Kafka, or if you've seen Kafka Quick Start, you typically say start Zookeeper cluster, start the Kafka cluster. With KRaft, if you want, you can just do one single thing. You just start the Kafka cluster and you set the roles of the Kafka nodes. Now let's compare the scenarios we looked at previously as well. So the controller failover scenario. When the active controller fails, the other followers or the other controllers have a in-memory information of all the data already. So the controller failover is pretty instantaneous. And that basically means that when a controller goes down, you no longer have to create a new controller, or do a new controller and load all the data from Zookeeper into the controller, because that data is already there and it's pretty instant. For broker restarts as well, brokers are efficiently fetching only the required metadata. That's changing using a pull model. In the previous model, the controller had to update the metadata and then go and replicate all the metadata back to all the other brokers. And while it was a bottleneck, it also meant that everything was controlled by the controller here. In this case, the brokers can all efficiently pull what's changed, what's the delta all the time. And that's business as usual for Kafka topic, essentially. So this is something that Kafka is really good at, and they're leveraging that capability for managing its own metadata. It also gets rid of any sort of RPC calls that were being made between Kafka and Zookeeper, and everything is handled in an event-based model. And lastly, there's a unified security model to where the metadata is stored and how it's secured and how the Kafka topic data is stored. Because previously they were in two different systems, they had a different security model, and this didn't help in that sense. Okay, so moving on to the tools. I probably didn't show in one of the previous pictures, but one of the other challenges was also that Zookeeper had its own Zookeeper shell, which was really useful in managing and understanding, but an admin could change the state of the cluster using the Zookeeper shell. And that was another reason the controllers and the state in the Zookeeper could get out of sync. So controller is not the only path for getting data into Zookeeper. Now, with KRaft, there's a new metadata shell. And this basically replaces the Zookeeper shell and provides you similar capability, but it constructs a virtual file system with cluster information and allows you to inspect the data. So you can see things, but it doesn't add the extra burden of changing data under the covers. There are some other things like dump log segment.sh. This is again a Kafka utility, which can be used to debug the log segments and snapshots for the cluster metadata directory. And finally, there's the Kafka metadata quorum.sh, which is used to describe the runtime state of the cluster metadata partitions. So these are some of the new tools that Kafka have added to Kafka itself to complement or to allow the management side of things with this change going through. Now let's look at the migration. So while this is a significant change, this is not completely backwards compatible. So there is a migration involved, and the migration is a one-off activity, and we'll work through the stages of the migration here. So there, like at a high level, there are 4 stages to the migration process from a Zookeeper-based cluster to a KRaft-based cluster. And the first phase is initialization. So you start a dedicated set of KRaft controllers, which are Kafka nodes, alongside an existing Zookeeper-based Kafka. Step 2 is to kick off the metadata migration. And with this, you are telling Zookeeper to send the data off to the new KRaft controllers, and the KRaft controllers start loading all the information from Zookeepers. Once that is ready, the Kafka cluster basically enters into a dual write mode, in which the brokers are writing metadata to KRaft controllers, and the KRaft controllers will in turn write the data to Zookeeper as well. So the Zookeeper state is maintained, but KRaft is the primary path for the data move. And lastly, the finalization step, which is the KRaft controller stopped writing the data back to the Zookeeper, and the Zookeeper is completely removed from the deployment. I'll show these steps in a bit more detail in the next few slides, so hopefully it'll become a bit more clear. But I just wanted you to understand, you start a new set of controllers, you migrate the Zookeeper data into the KRaft, and then you configure your brokers to talk to KRaft as the primary, and Zookeeper is maintained. So you enter the dual write mode and then the finalization. So let's see how this would look like. So here you've got 3 brokers and 3 Zookeeper pods, and the metadata is flowing from brokers into the Zookeepers. The next step, the brokers, a new set of KRaft controllers are added. And the thing to keep in mind here is there are additional resources being used during the migration because you are now running 3 additional things. So there is an increase of resource required during the migration process. Once the migration is complete, you will not have that additional need, but during the migration, you do need additional things. Another thing to note is when you're doing this migration, these new controllers need to be dedicated controller nodes. So if you go back and remember, I said you have dedicated roles, and you can have shared roles where a Kafka node can be a broker and a controller. For the migration, you have to start with a dedicated set of nodes, and I'll mention towards the end how you move from there on. But once you've migrated, you can update the brokers to then take shared roles if you want it. But for the migration process, they must be dedicated. And the brokers will then perform a rolling update. So everything is still available. That's one other thing I want you to keep note of. During the migration, while you need additional resources, and your brokers and controllers will be restarted a number of times, at no point the service goes down completely. Your brokers are always rolled incrementally. So when you do a rolling update, one broker is updated at a time, and that means that any partitions that need to be served from that broker are moved to another broker, and the other brokers will continue to serve. And this is typically how Kafka does rolling updates for Kafka changes and things like that anyways. So here the brokers then get registered as KRaft brokers with the controller, and the metadata migration has started. Once the metadata migration completes, the brokers start migrating into this flow. So if you see the difference between here, the brokers are registered, but the data is still going to Zookeeper. Once the metadata is there in Zookeeper, you move into this mode, which is the brokers are now writing to KRaft controllers, and the data is being written back to Zookeeper as a dual write. And in this mode, the brokers know nothing about the controllers, nothing about Zookeeper at all. They only know about KRaft controllers, and the KRaft controllers are writing to Zookeeper. So that's kind of your step-by-step migration path. Once you're here, you can start the finalization, and that means you basically remove the Zookeeper and you roll your Kafka controller, so they are no longer looking to write the data to Zookeeper. So you end up with same sort of structure that you had before. Once you're here, and if this was like a dev cluster and you wanted to reduce these or change them from dedicated nodes to individual nodes, you can do that. But during the migration, that's not possible. So again, once you back Kafka with KRaft, when you create new instances, again, you will create, and this is needing the usual resources again. There are no additional resources required once the migration is complete. Lastly, let's talk about KRaft with Event Streams. So as I said, Event Streams is an operator-based offering for deploying and managing enterprise-grade Kafka on Kubernetes platforms. There are a couple of changes we are bringing along. So there are operator channels that we use to provide new versions of Event Streams, and versions within a channel are always backwards compatible. So the way forward, and this is in line with how Kafka community and the Streamsy community, which is the Kubernetes operator Event Streams is based on, are all following. So up till a certain channel, like today, all the versions of Event Streams only support Zookeeper-based Kafka deployments. We have provided a tech preview of KRaft deployments since like March 2023, so for over 2 years now, but we're going to remove the tech preview and provide a production-ready KRaft in coming months. And the way it would work is there will be a new channel that will be introduced, which will have support for both Zookeeper and KRaft-based deployments. So a Zookeeper-based cluster can upgrade into this channel, and then there will be a semi-automated migration process. By semi-automated, I mean the users or the customers will be in control of when they want to trigger the migration. But once they trigger the migration, the operator will manage all those previous steps that we talked about. So you will say, OK, I'm ready to migrate my cluster, and it'll basically migrate all the data, get it into the dual write mode, and then ask you for the finalization side of things. And once you are with KRaft, you will be able to migrate to one of the newer channels, which will only support KRaft and not support Zookeeper at all. So if anybody who's aware, Kafka 4.0 is around the corner, and Kafka 4.0 is the version of Kafka that will completely remove support for Zookeeper. So moving forwards, and when you create new instances from here on, there will only be KRaft-based Kafka deployments that we would support. And that kind of brings me to the end of the content. Are there any questions people had? I was expecting a few more questions along the way, but I don't know if people are posting those questions on the channels. But if there are any questions around this content, or if you want to go over anything else, I'm here to help.
Well, I'm looking at the chat and I don't see any questions.
All right.
Can you? Okay.
Oh.
All right. So, okay, we're finishing up a little bit early, but that's okay. Give everybody a break between now and the next session, which let me just take a second here. And the next session, I believe, is what's new in MQ. Let's see. Okay, so yes, the next one is MQ, what's new in MQ 9.4 with Matt Lemming and Ant Beardsmore. And that session is going to start at it's going to start at 1 or well at looks like Luke, what time does the next session start?
All right, so our next session is going to be starting at 1:25 Eastern time zone.
Okay. All right, so 25 minutes after the hour. And don't hesitate, please, to answer the poll, the closing questions. And we will join back at 25 minutes after the hour for Matt Lemming and Ant Beardsmore on MQ 9.4. And we appreciate you joining, and we'll start the channel back up then. Thanks, Niraj. Good job. Appreciate it.
Thank you.